In this video, we will see potential due to a charged spherical shell. Okay, and there are three special cases in this. First, we are going to deal with a point P when it lies outside the shell, and second, we are gonna deal with a point P when it lies inside the shell, and then when it lies on the sphere. So this is the conducting spherical shell. This is the sphere. The ray origin O and the radius R. Here it is with the radius R, capital R. And we know that sigma is the surface charge density, and then the total charge is the Q. It is present on the surface, and then we want to find out the potential at an external point P. Here is a P. Here we want to find the potential from the distance R from the center of the spherical shell is the origin, that is marked as O, and from here, from origin to P, this point, the radius is small r. And now what we are going to do is we are going to divide the spherical shell into a number of rings with centers of OP. Consider one such ring A, B, C, D. So this is A, this is point B, this is C and D. So these four we consider one such spherical ring. So we have used onion for cooking. So if we cut it into two pieces, we get a like spherical concentric shape like structures, and the thickness of that width of the onion peel, it will be like this. So this segment, and that arc length also we can calculate it, that is AC is equal to R, the radius of the circle, into d theta, that the angle that makes with this segment. Okay, then the circumference of the ring, we know that it is 2 pi into CE. For CE we calculate, we take this right angle. Which right angle? This O, E and C. So from this we calculate that sin theta is equal to CE by OC, that is equal to CE divided by R. OC is nothing but the radius of the circle. So we get CE is equal to R cos theta. So we have the arc length, that is R d theta. Then we have the circumference of the circle, that is 2 pi R sin theta. Then we also find the area of the ring, that is circumference into thickness. That will come into, already we have the circumference, that is 2 pi R sin theta, into thickness is this R into d theta, that is the thickness of the ring. So the final equation will be 2 pi R square sin theta into d theta. Now we have to consider the charge on the ring ABCD, that is for a small segment dq. Then we will integrate over it and we'll find the charge for the entire thing, that is Q. First, to find this charge on the ring ABCD, that is dq, first we will find the from the formula, charge on the ring is equal to area of the ring into surface density. Area of the ring we know, surface density is sigma. For sigma we substitute the total charge on the shell, that is Q, divided by the total surface area, that is 4 pi R squared. Then substituting for this sigma, we get the charge on the ring ABCD dq, that is the small ring charge. For the charge that we find using that small ring, that is dq is equal to, we just substitute this one, 2 pi R square sin theta d theta into Q by 4 pi R square. So this 2 and this 4 will get cancelled, and pi will get cancelled, and R square and R square gets cancelled. So finally we have Q sin theta d theta divided by 2. Now we note that every point on the narrow ring ABCD is at the same distance x from the point P. So we can note that in this, so every thing is at the same distance. So we find the potential dV is equal to 1 by 4 pi epsilon naught dq divided by sec. Instead of this dq, we substitute the value we have find, that is q sin theta d theta divided by 2. And then finally we get q sin theta d theta divided by 8 pi epsilon naught x. Furthermore, we have this triangle CEP. Okay, from where do we get this? So here in this triangle, okay, we have the triangle OCP. So from this triangle we just have this small segment of the triangle, and from that we infer that x squared is equal to CE squared plus R minus OE squared. So this is from the Pythagoras theorem, and so x squared is equal to CE squared plus R minus capital R cos theta will come. For this OE we can substitute capital R cos theta. Okay, and then how does it come? So cos theta is equal to, like here I write here, cos theta is equal to OE divided by OC. That is equal to, what is OC? OC is the radius of the circle, that is capital R. So it will become OE divided by capital R. So we take it to the other side, that for OE is equal to, so I take this capital R this side, R cos theta. Okay, so therefore we substitute for OE. So here in this derivation we have x squared is equal to c squared plus r minus OE squared. So for this OE we just substitute the calculated value of OE, that is r cos theta. So and then we expand the equation a minus b the whole squared. What is the formula? A squared plus b squared minus 2ab cos theta. So using that formula we expand this equation, and then we have x squared is equal to r squared plus small r squared minus 2rr cos theta. So here then we differentiate equation 2. So what happens when we differentiate x squared? It is 2x dx is equal to, so what happens when we differentiate this with respect to x? So we have 2rr sin theta d theta. So sin theta d theta is equal to x dx divided by capital RR, obviously. And then what we do is we substitute this equation 3 in first equation. Okay, so we have in first equation, that is dv is equal to q sin theta d theta divided by 8 pi epsilon naught x. So in this we substitute for sin theta. Okay, sin theta is equal to x dx divided by capital R, that is equal to qx dx divided by 8 pi epsilon x r. So we are taking this sin theta d theta term, in that we are replacing this value. So after finding the potential, we just integrate over the limits r minus r and r plus r. So what we integrate this equation, q dx divided by 8 by 4 into r. So what happens is, this constant we can take it out, q divided by 8 by epsilon naught rr, we can take it out, and we are just integrating this thing. So finally we will have to substitute for r plus r minus r. So what happens? We get q divided by 4 pi epsilon naught r plus r minus r minus, this small r and minus r, it will get cancelled off. We have only r and r, so that is equal to 2r. So therefore v is equal to q by 4 pi epsilon naught r. So this expression is the potential for the total charge, that is concentrated at the center, Okay, and then we find also the potential charge for the point lying on the surface, that will be 1 by 4 pi epsilon naught q by capital R. So what happens if the point P lies inside the shell, then we integrate it over from minus plus, I'm sorry, capital R minus R to capital R plus R. Then we have the equation q by 4 pi epsilon naught this R. Okay, so this is same, this will be, this potential on this will be the same as the potential on the surface, that is potential of the point lying inside the shell will be same as the potential lying on the surface, that is 1 by 4 pi epsilon naught R, whereas the potential outside the sphere will be equal to V is equal to q by 4 pi epsilon naught small r. So that makes the difference here. Okay, thank you.